So we are going to continue with our lecture series. This would be lecture 18. Now, I would like to first rectify one of the mistakes that I did in lecture 17. This was about an example that I did, and I'll show you what the mistake was, which was leading to the wrong solution. So, this example was about finding the null space of a matrix, and I had given the following matrix. So this was my matrix A, and it was reduced to an echelon form. It looked something like this. Okay, so I'll tell you what my mistake was. This is the so-called echelon form, so let me denote it by U. I'd use the word R because I somehow thought in my mind that it is a reduced row echelon form, but it is not. It is just an echelon form because, as you can see, this entry out here too is a pivot entry. So it's technically not a row reduced echelon form. So the pivot columns are as follows. If you see, there is a pivot over here. So first column is a pivot. As you can see, there's a pivot over here. So the second column is a pivot. And as you can see, there's one more pivot over here. So the fourth column is a pivot. So what are the free columns? So the free columns are the number third and the number fifth. So two free columns and two pivot columns. So that changes a lot of things that I said last time. So let me redo everything. So what should be the basis for the row space of A? Remember, we can get the information from the echelon form itself. So last time I said it will be two-dimensional because mistakenly I forgot about this as my pivot column. However, with this fix, we can now claim that it is going to be a three-dimensional space. Again, let me repeat one thing, that there are three pivot rows. If I know what are the three corresponding pivot rows over here, then I could have used this also as a possible basis. Since I do not know what operations I have done, so right now I can't be sure that I did not make a swap, because of which I can't just simply say first, second, third rows are going to be the basis. It might be first, second, and fourth row if there was a swap involved. Now what about the basis for the column space of A? Basis for the column space of A. This will also be three-dimensional because there are three pivot rows. But remember, I can't use this matrix. I have to come back to the original matrix because the column space of this guy and its reduced form are not the same. What is same in both the situations is the pivot columns, the first, second, and fourth. So I can use the first column of my original matrix, 1, minus 1, minus 2, 3. The second column, which is this, and the fourth column, which is this. So as you can very well see, the basis for the column space of A is also consisting of 3 vectors. Rank is 3, so the dimension of both the row space and the column space is 3. And these will also be the basis for the column space of A transpose and the row space of A transpose. Okay. Now the question was, what about the null space? Remember, null space is determined by the number of free variables. The dimension of the null space is the number of free variables, which in this case is 2. So my null space has to be 2-dimensional. Okay. And basically it is the third and the fifth column which are going to help me figure things out. So for null space, I know that the solution system for Ax is equal to 0 is the same as solution system for Ux is equal to 0. Both have the same solution set. So I will use the echelon form as follows. Okay. Remember the first, second, and fourth columns are the pivot columns. So basically, x1, x2, and x4 are my pivot variables. So I will express every pivot variable in terms of the free variables in order to get to the null space, the basis for the null space. Okay. So x1 can be written as minus 4x2 minus 8x3 minus 5x5. x2 can be written as minus 5x3 plus x5, and x4 can be written as minus 4x5. So remember, x1, x2, x4 has to be expressed in only x3 and x5. So I have to make one more substitution over here, which is basically minus 4 times whatever is x2 . See what does it give me. This gives me 12x3 and minus 4x5 minus 5x5 gives me minus 9x5, and rest of it is fine. So now we can come up with a solution. We can say right, multiple of 2. So this should be 5 halves, this should be 1 half, and that changes quite a bit. Make some changes. This will give me 2x3 and this will give me minus 7x5. Okay. Now we can go with the solution how will the solution set look like? So let's see. Any solution for this system will look something like this. X1 is 2x3 minus 7x5. X2 is minus 5 half x3 plus 1 half x5. And x3 is a free variable, x4 is minus 4x5, and x5 is a free variable. So I can write this whole thing as 2 minus 5 half 1 0 0, and I can write, split this as minus 7 1 half 0 minus 4 1. Okay. So once we are able to write this, then we can say any solution would be just a linear combination of these two vectors. As you can see, they are both linearly independent. So we have a basis for null space of A. And that basis consists of these two vectors. So the basis is two-dimensional, as one would expect, because the column space is three-dimensional and the total number of columns is 5. So this is basically the correction from the previous lecture. So now this is the correct solution, because last time we had made that error by not identifying this as my pivot column. So now we'll proceed from here to the next topic, which is basically about determinants. So we'll try to find out what determinants are, how do they behave, and what all things can we do about them. How are they helpful to us? Okay. So the next topic is that of determinants. And what determinants do for us is something very, very counterintuitive. Determinant is actually just a number associated with a matrix. And that number can tell you quite a few things about the matrix that it is associated with. However, determinant is only defined for square matrices. So this thing is a bit of a restriction, but still, it's not that bad. It can give us what we are exactly looking for. So what exactly is determinant? You might have seen determinants in different contexts, or maybe in multivariable calculus. We just tell you, oh, this is how you compute a determinant, but that is not actually the real story. Determinant is, in fact, a function. So determinant is a function from the set of square matrices. So suppose I have a matrix, set of matrices, all matrices of size n by n. And let us say all these matrices were given on the set of real numbers. That means all the entries are real entries. So determinant is a function from the set of square matrices to the set of real numbers. If your matrix has complex entries, then the determinant would be a function from matrices to complex numbers and so on and so forth. Depending on whichever field ring you are on, determinant would map to that particular field or ring. But what kind of a function is it? It's not just an ordinary function. It's a function which should have these properties. It is linear in each row of A. So suppose we are trying to find the determinant of A, where A is a square matrix of size n by n. Then it should be linear in each row of A. What does that mean? I'll tell you in a moment. The second thing is determinant of an identity matrix should be 1. And the third property it satisfies is the determinant of my matrix is 0 if two rows of A are the same. So I want a function from my set of matrices to the set of real numbers which has all these three properties. There's a fourth property which actually is just for convenience, although it follows from the first three. So the fourth property is that the determinant of A is the same as, let me rephrase it. So suppose I start with a matrix A and I make a row swap and I get a matrix B just by one row swap. Then the determinant of B must be the negative of the determinant of A. So whatever determinant of A is, it is minus of that. Okay. As I said, these three properties are capable enough to give you determinant. The fourth is an outcome of these three properties, but we will just, for the sake of argument, we'll keep the fourth one. It's a nice property to know. Question is, fine, I have this function. I'm trying to create a function which has all these properties, but what does that function look like? And will there be more than one function? First, I'll convince you that there are such functions, and then I will convince you that the function that I'm using is the only function which can have these properties. So in some sense, determinant becomes a unique function if I force it to have these properties. There cannot be any other function. But before I proceed, I should try to explain to you what I mean by linearity in each row. So let me first deal with a 2 by 2 case, where we have matrices of size 2 by 2. When we say linearity in each row, so imagine I have a matrix A, B, C, and D. And you want to talk about the determinant of this thing. By linearity, I mean is as follows. Let's suppose you give me A plus U, B plus B, C, D. Then linearity means the determinant of this matrix would be the determinant of A, B, C, D plus the determinant of U, V, C, D. So linearity in each row means it would be a linear, it would act as if like it's a linear transformation on each of its row, provided the other rows remain constant. Or it also means the following thing. Remember, we are talking about linearity. So suppose I have A alpha, B alpha, C, D. This would mean it is alpha times the determinant of A, B, C, D. So this is what we mean by linearity in each row. Okay, now that we have understood this, I'll first give you a candidate function that you might be familiar with. Okay, so let's try to find out determinant of A, B, C, D. Okay, I'm dropping the square brackets. It's kind of inconvenient to write it. Okay, so how do we want to proceed? Let's see. Now, okay, so first let me give you a candidate function, and then I'll show you that this is the only function which can satisfy all these three properties. From some class in high school or maybe in multivariable, you might know that determinant, we say, oh, it's AD minus BC. Does this function satisfy everything that we know we are requiring of it? Let's see. Is it linear? Is this function going to be linear? So let's try. What would be the determinant of A plus alpha U, B plus alpha V, C, D? According to this formula, it would be A plus alpha U times D minus B plus alpha V times C. So this would be AD minus BC plus alpha times UD minus BC. And if you look at this, this is nothing but the determinant of AB, CD plus alpha times the determinant of UV, CD. And this is exactly what we had talked about as the linearity in the first row. You can similarly prove the linearity in the second row. So of course, this function seems to be satisfying the first property. It is linear in each row. Even though I have shown it only for the first row, the same idea works for the second row. What about this guy, 1, 0, 0, 1? By this formula given to us, this would be AD minus BC. So it would be 1 times 1 minus 0 times 0, and this would be equal to 1. So that function, that candidate function does satisfy the second property also. What about the third property? Determinant is 0 if two rows are the same. So let's say if I was computing determinant of AB, AB, according to this formula, it should be AB minus AB, which is 0. So whenever two rows are the same, the determinant is definitely 0. So our candidate function does satisfy the three properties, and you can check it satisfies the fourth property also. But let's not worry about it at the moment. Question is, that function is one function that I gave you, and I showed you that these three properties are true. Could there be some other function, maybe perhaps A plus D minus B times C or something like this, which could satisfy these three properties? My claim is that that is the only function AD minus BC which has all these three properties. Hence, if you want determinant, then that is the only formula for determinant of a 2 by 2 matrix, and there could be none other. So how do I convince that such is the case? Well, let me see if I can convince you with some ideas, and then we can proceed. Okay. So how do I convince you that that is the only way it is going to work? Let me try. So suppose I start with my matrix A, B, C, D. Then so here is a possible way that we might be able to get some information. So this is something that you should definitely try to complete. It will give you practice in linearity also. I can definitely write my matrix ABCD as some of those 4 matrices. Now, if I can prove something about these matrices, the ones which I listed, perhaps they can tell me a little bit about what I can talk about as the determinant of my matrix ABCD. But the question is, what exactly can I say about the determinant of those matrices? And how will it help me identify the determinant of ABCD? So the real question is, how do I deal with the linearity property? For example, is this splitting linear? Well, if you look at it, it's technically not linear. However, if I try to write it in a slightly different way, then things might be. For example, can I write it like this? AB 0, 0 plus 0, 0 CD. Can it help me somehow? So think about these kind of splittings and see if you can talk about the determinant of those kind of matrices, and hopefully that will help you understand why AD minus BC is the only way out of this thing. Otherwise, if you can't get it, I'll show you how to deal with the linearity property. But it's a good exercise just once to try to do it on your own. Okay.
28 minutes.
Okay, so there's something more about determinants that I want to first talk about. Why is determinant such a useful thing for us? So the first question we have to deal with is how to compute determinants. Now, just so you know if I was given a determinant of a 3 by 3 matrix, then again I want my function to satisfy all these three properties. After some lot of manipulation, you can convince yourself that the form would look something like this. This is how it will look like: A11 times A22 minus A33. Sorry. A11 times A22 A33 minus A23 A32 plus A12 times A23 A31 A21 A33 plus A13 times A21 A32 minus A22 A31. So if you go through all these three properties, then I claim that that is the only function which can satisfy all these three properties, hence it's the determinant function. Getting to this is not much fun. However, you should see there is something going on in here. If you focus on these entries, 1, 2, 3, 1, 2, 3, 1, 2, 3. So it's like all possible permutations of 1, 2, 3 that we have written in here. And some of them are coming with a positive sign, some of them are coming with a negative sign. So in all there are 6 terms, which is 3 factorial. So if you write determinant of a 4 by 4 matrix, if you expand it and write it in this full glory, it will turn out to be having 4 factorial terms, all possible permutations on 4 indices. So definitely this is not the way we would want to compute the determinant, because very soon for 4 by 4, 5 by 5, there will be way too many terms to handle. So we want a much better approach than these kind of formulas. So what are those approaches that can help us compute the determinant better? One of them is what we call as the cofactor expansion. It was introduced by Laplace. So we'll discuss what is a cofactor, what is a minor, and how will we use that to compute determinants. Okay. So let's first talk about minor of a matrix. And we will denote it by Mij. Then we will talk about the cofactor of a matrix, which we will denote it by as Cij. So minor of a matrix is basically the determinant of the submatrix obtained after deleting the ith row and jth column. Okay. So for example, if you look at the following matrix, let me have simple matrix, say 1, 2, 3, 4, 5, 6, 7, 0, 0, something like this. So the M12 minor would be the determinant of the matrix that I obtain after deleting the first row and the second column. So if I delete the first row, which is this row, and the second column, then whatever matrix is, submatrix is left, the determinant of that is what I call as my minor 1, 2. And using our knowledge of a 2 by 2 matrix, this will turn out to be minus 42. So M12 turns out to be minus 42. Let's do one more. What would we say M33? It would be the determinant of a matrix obtained by deleting the third row and the third column. So it would be the determinant of the matrix 1, 2, 4, 5, and whatever that turns out to be, which is minus 3. So for each entry, for each pair I and j, we will have a minor of my matrix. So in all, we will have 9 minors for a 3 by 3 matrix, and we can compute them one by one at a time. Now, what is the cofactor of a matrix? Well, cofactor is also an interesting thing. Cofactor is what I like to call as minor with a sign. Okay. So cofactor is what I like to call as the signed minor . Okay, which is basically minus 1 to the I plus j times mij. So for example, if I wanted the minor C12 for this matrix, it would be minus 1 to this power of M12, which is minus times M12, which would be plus 42. What would be C33? C33 would be minus 1 to the power 3 plus 3, M33, which is same as M33. So cofactor is nothing but a signed minor. Okay. So what Laplace said was that if you can find these cofactors, that means if you can find these minors with a sign, then you can compute the determinant of a matrix using the signed minors. So his idea was a bit recursive, that if you start with the n by n matrix, you can reduce the problem of computing the determinant of an n by n matrix to that of computing determinant of a n minus 1 by n minus 1 matrix, and you keep doing it iteratively until you are in a place where you can do things nicely. So this is what Laplace's idea is, and I'll show you how to use Laplace's idea. So as we shall see, Laplace's idea is good for computation purpose, but it is still not what we are after. Still there are things which can be done better, and then if you use it in combined with Laplace's idea, then things turn out to be much more simpler and elegant. But first let us see what is Laplace's expansion. So this is what he said. You want to compute the determinant of a matrix, then you choose a row or a column, whichever row and column you can want, just choose a particular row or a particular column. Then you compute the cofactors with respect to that row. And using them we can find the determinant. So these are the first two things that you have to do. So what I'll do is I'll first illustrate it on an example what he meant, so that it's easy for us. So he said the following thing. Suppose you have a 3 by 3 matrix. Given by this, then if you want to compute the determinant of this matrix, first choose a row or a column. So let us say I choose the third row. Suppose I chose the third row. Then you compute the cofactors with respect to that row. That means I want the cofactors C31, C32, and C33. And once I have those cofactors, then I can use these to find my determinant. So what would be those cofactors? So say C31 would be basically -1 to the 3 plus 1, M31, which is the same as M31, which is the determinant of the matrix obtained by deleting the third row and the first column. So it would be A12, A13, A22, A23, which turns out to be A12, A23 minus A22, A13. So likewise, you can get your C32 and you can get your C33. Once you have all those things, then Laplace said the determinant of your matrix would be basically each entry of your row multiplied by its corresponding cofactor. So the determinant would be A31 times C31, A32 times C32, A33 times C33. So this is how you will get the determinant of your matrix. The good part is you choose any row or any column. Just once you have made that choice, then you stick to that and find all the relevant cofactors. And if you combine them this way, you will get your determinant. The proof of Laplace's expansion is not something very elegantly that can be given very elegantly here. Elegant proof requires something which we don't have at this stage, at least not in this course. So I won't try to prove it here. However, it's a nice thing to look at how the proof runs, even in the non-elegant case. There's something nice about this proof that you should be able to okay. So let's try to do it on an example and see what's the determinant of. So what is the determinant of something like this? If I want the determinant of this matrix, let me choose some row. Let us say if I choose the second row. So I will go with the following cofactors, C21, so it is minus times the determinant of the matrix obtained by deleting the second row and the first column. So second row and the first column will give me 2, 3, 0, 7. Likewise, I can now compute C22. C22 will be minus 1 to the 2 plus 2 M22, which is going to be the determinant of the matrix obtained by deleting the second row and the second column. So it will be 1, 3, 5, 7, which is minus 8. And then I'll get C23. Which would be minus times the determinant of the matrix obtained by deleting the second row and the third column. And this will turn out to be 10. So according to Laplace, the determinant of our matrix would be 0 times C21, 1 times C22, and 3 times C23. So C22 we just found is minus 8, so it is minus 8 plus 30, so the determinant must be 22. So this thing is something that, if you notice in this particular example, this entry being 0 is quite helpful for us in computation. So the moral of the story should be that we should try to expand it along that row or column which has the maximum number of zeros, so that we can cut down on our computation. And this is going to be the key in computing determinants. We'll try to do something so that we can produce more zeros in a matrix, and thereby reducing our overhead with calculation and cut down on the number of operations. It means stop it.